All right, here is problem number 6 on applied optimization. And this one we're going to look at the quickest route to get somewhere. And I know this is going to take us a while, so it won't seem like the quickest route, but it's how we can use calculus to come up with this. So Ariel, who is in a rowboat 2 miles from point B on a straight shoreline, notices smoke coming from her house, which is 6 miles down the shoreline from B. She can row 6 miles per hour and run 10 miles per hour. How should she proceed to get to her house on the shortest amount of time? Well, let's first of all draw a picture here of what this might look like. So what we're going to do here is, I'm going to put the shoreline right here. So here's our shoreline right here. Okay. And they said Ariel, who's in a rowboat 2 miles from point B on a straight shoreline. So here is point B. And we're going to say Ariel is out here. So here's A for Ariel. So she's this far, and she's 2 miles from point B. So here is 2 miles. She is from the shoreline, okay? And so she's in this rowboat here. So let me do my fantastic little thing here. So here she is in a rowboat, and she's out here on the water, okay? Notice the smoke coming from her house, which is 6 miles down the shoreline from point B. So we'll say her house is here. So this right here is 6 miles from point B down here to her house. And her house is right here, and she notices smoke. Here's her house, and there's smoke and fire and all sorts of stuff coming from her house. So she's figuring, how can I get there the quickest? So she can row 6 miles per hour, okay, and she can run 10. So I guess what they're asking you is, should she row straight here to the left and then run down? Or is there some point, where we don't know where, that she can kind of row at an angle and then run the rest of the way that would be quicker than going straight and down, you know, kind of cut that off. So that's basically what we're trying to do. So we're doing the shortest amount of time, so time is what we're looking for. First of all, let's kind of label this whole thing. So I'm going to move this 6 miles down a little bit, or out a little bit, so this doesn't confuse you. So here this is 6 miles. If this whole side is 6 miles, if you will, if I call this X here, because I don't know where she's got to hit the shoreline to start running this way, and this part here would be 6 minus X, that would count for this whole side. And we know this is 2 miles here. So we can actually figure out what this distance would be with an X in it, if you will, because this is a right angle. But first of all, let's kind of set up what we want for time. So this is going to have 2 legs in our journey, so we're going to say time equals, now we're going to have, and oh, before I do that, we have to remember that distance equals rate times time. So if we're going to be doing all this kind of stuff, we're basically trying to find the shortest time. If I divide by r on both sides, I know that time will equal distance over my rate. So I'm going to have 2 legs in here, so I'm going to do distance over the rate plus distance over the rate, all right? The other thing is her rate for rowing, okay, is 6 miles per hour. And for running is 10 miles per hour. So that's our rate right there, okay? So we just got to do distance. So I'm going to do the first part of the rowing part. So I'm going to do distance over the rate. So the rate for the rowing is 6 miles per hour. So I'm going to put a 6 down here. But I have to put the distance. Well, the distance that she's going to row is going to be whatever this is right here. So I'm going to do it. So she's going to row from here to here, okay? How would I do that? Well, I can do the Pythagorean theorem. So I know that x squared plus 2 squared equals c squared. Okay, so c squared is going to be, if I take the square root of both sides, or c is going to be the square root of x squared plus 4. So that's really what that side is right there, and that's the distance of it. So I'm going to put square root of x squared plus 4. All right, so here's my distance, if you will, over my rate. So there's the time of the first leg of our journey, right? Plus the second is once she hits the shore right here, she's going to run the rest of the way. So she's going to run all the way down here to this. So what is the distance on that one? Well, the distance is easy on that one. It's 6 minus x. I don't know what it is, but I know it's 6 minus x. And she runs 10 miles per hour. All right, so now there's our time equation. So here's her rowing part of her journey. Here's her running part. We just got to figure out where's the optimal place for her to hit the shore to get down there, right? So I'm just going to kind of rewrite this a little bit. So our time equation is going to be, pretend there's a 1 here, is 1/6, and I'm going to change that to x squared plus 4 to the half power, just so, because we're going to take the derivative. We're looking for the optimal, and this would be 1/10 times 6 minus x. Okay? So if I'm taking the derivative, because I want to know dt dx, if you will, or t prime, okay, this is the power rule, so that'd be 1/12 times x squared plus 4 to the negative 1/2 times the derivative of the inside, which is 2x, plus, if I take this derivative here, I can actually multiply this out. So 1/10 times 6 is 6/10, or a constant, and this would be negative 1/10x, so it's going to be actually negative 1/10. Okay? Now, when I go to do this, down here, I'm going to see that, okay, I can see the 2's can cancel here, so this will cancel 1, this will be a 6. So I end up getting, okay, I'm going to rewrite this term right here. So I have x on the numerator over, and the 6 would be in the denominator. I'm just going to rewrite this what it was, x squared plus 4. And this we're going to put equal to 0 because that's how we find the optimum that it's going to be. So if I move this over here, it'll be equals 1/10. So let me kind of go through what I did. I did the derivative, then I rewrote it. So here's my x right here. That's what's on the numerator. The 6 right here is down here in the denominator, and I just rewrote this right here to put it back down here. Alright, so there's that term. Here, I just moved, I'm going to use a different color here, this term right here, I just moved it over to this side over here because it's equal to 0, so I can come up with this. Alright, now I'm going to cross multiply to solve. So I have 10x equals 6 radical x squared plus 4. And I'm solving for x, so I'm going to square both sides. So if I square this side, squared this side, I have 100x squared, okay, is going to equal 36, because don't forget you got to square the 6 times x squared plus 4. And then I'm going to be solving for x still, so I'm going to do the distributive property here. So I have 100x squared equals 36x squared plus, and then 36 times 4 is 144. Then I'm going to put the x squared on one side, so I'm going to subtract 36x squared. So I have 64x squared equals 144. Divide by 64 on both sides, so I have x squared equals 144 over 64. Then I'm going to take the square root, and when I do that, I have x equals 12 over 8, which is reduces to 1.5. Now when we're talking about 1.5, what does 1.5 stand for? Well, that's going to be the miles, because that was the distance that she has to row down to the shore. So that's kind of interesting. So let's come up here. So now I know right here, this, excuse me, let's undo this. This right here is 1.5. So that means if she rows kind of on an angle here, hits the shoreline at 1.5, and then down here, if she runs the rest of the way, which is 4.5 miles, then she'll get to her house in the shortest amount of time. Now I know after we did this that probably the house would be burnt down, but I'm just showing you this is a way you can figure out the most optimal place to row to get to her house. And the other thing that also, just before I finish this problem, it makes sense to me that she's going to run more than she's going to row to on the shoreline because she can run faster. So I kind of thought that makes sense to me because her rate of running is much faster than her rowing. Well, that's this problem.